Alright, so if you need to, pause the video for this one. I won't read it to you, but I'm just going to go ahead and jump right into it. So here we have a diagram. It has a box of 25 kilogram. It is resting on a smooth horizontal surface. You have two forces, one that's pulling on the box. So this is F pull. In the statement is given at 65 newtons at an angle of 37 degrees, which is right there. And then you also have a second force that is pushing down on it, which is angle at 20 degrees below the negative x-axis as shown here. And F push here has a magnitude of 82 newtons. So keep that in mind. So the left arrow is 65 newtons. The right arrow is 82 newtons. And it wants us to do A, B, C, D, and E. All right. And we'll just get cracking. I'm going to do part A and B on this one. It's just to draw the free body diagram for the box. And it says to make sure the lengths of the vectors representing each force are qualitatively correct. So essentially what just wants to just be a little more careful when you draw this thing or these vectors. All right. So to draw a free body diagram, I'm just going to use little dot, and then all your forces should be starting from the dot and then radiating outward. All right. So the first vector I'm going to draw is F pull. I'm just going to call that F pull. So as you can see, F pull here mirrors the force in the diagram. And then the next one I'm going to do is F push. But you notice here, F push is a little longer than F pull because F pull is 65 newtons. F push though is 82. So I drew 82 longer than 65. And this is what it means when it says qualitatively correct. So essentially just don't be sloppy and just draw arrows. You have to make sure the length for the most part represents, what these vectors need to be in terms of magnitude. All right, the next thing I'm going to draw is F of G. As you see here, F of G is much longer than F push. So if this length here is already 82 newtons, well, F of G is about 250 because if you look at the box here, this is 25 kilograms. And if I just round up gravity due to acceleration to about 10 meters per second square, 25 times 10 is 250, right? I know it's not 250, but it's about 250. So therefore, I'm going to draw F of G much longer than F push. And this is, again, qualitatively correct. Asks for pretty much the length of the arrow to, represent it fairly accurately. And then last but not least, the box is resting on a horizontal surface. Therefore, I know there's a contact force exerted by the floor onto the box, which is pointing upward in the y direction in this case, and this is F of N. And F of N here is just slightly shorter than F of G, or, it has to be bigger than both of these because it should resemble F of G about. It's not equal to. The math shows that it doesn't equal, but here it says qualitatively, so I'm just going to draw it about F of G. But if you actually look at it, it's just a little shorter. All right. Here, part B asks us to find the horizontal and vertical components of the forces for F pull and F push. So here I'm just going to list everything. F pull in the X direction is pointing leftward because this particular F pull vector is pointing northwest, which would suggest going left and up. And then the F pull in the Y direction here is going to go point upward. And then I'm going to do the components for F push. F push again is down and left. So it has to go left. So F push in the X direction is left. F push in the Y direction is down. And then let's go ahead and set it up. It wants us to find these four things, right? It says components. So these are your components using dash line. So I want to set up the components for F pull on the left first. So no particular order. I'm just going to go from left to right. So here's F pull, which is pointing left and up. So to find F pull X and F pull Y, I just need to do sine and cosine. All right. So in this particular diagram, F pull X is the adjacent leg to this angle. Adjacent would suggest that I need to do cosine. Cosine of 37 is adjacent, which is F pull X over hypotenuse, which is F pull. And that's where the statement comes from, right? Cosine at 37 degrees, which is adjacent over hypotenuse. So if I were to solve for F pull X, I would multiply both sides by F pull, or I can just literally move this F pull up to the left numerator, which is the same thing as multiplying both sides. So now I have an expression for F pull X. So F pull X is simply F pull, which is the hypotenuse times cosine at 37. And then F pull is given in the statement at 65 newtons. So I'm going to plug that in my calculator, and I'll get a value of I'll get a value of 51.91 newtons. But you notice here I highlight the negative sign because Well, when you do the math, you're really just calculating the magnitude. But whether it's positive or negative really just comes from common sense. If you drew your components correctly with the arrows, Fpull in the x direction here is pointing leftward. So you need to indicate that it's pointing leftward by a negative sign. All right, I'm going to go ahead and do the Fpull in the y direction. Fpull in the y direction is pointing upward. Now, in terms of sine, cosine, or tangent, I'm going to use sine because Fpull in the y direction is the opposite leg of this angle that's given as 37. So I'm going to do sine of theta, which is 37 degrees, which is equal to opposite over hypotenuse. And my opposite in this case for this triangle on the left here is Fpull in the y direction. Once again, my hypotenuse is Fpull. So if you solve for Fpull y, you have to multiply both sides by Fpull, just like we did with the left side. Therefore, Fpull in the y direction equals Fpull times sine of 37. But Fpull, once again, is given as 65 newtons in the statement. And if you simplify that on your calculator, you get a magnitude of 39.12. But here, I include the direction positive because it is pointing upward. All right. Other than that, you would do the same strategy for the Fpush in the x direction. The angle that's given here touches the horizontal axis, which is 23 degrees. So Fpush x here is my adjacent to this angle. Because it is adjacent, I will do cosine of 23. So cosine of 23 is equal to adjacent, which is Fpush in the x direction, divided by Fpush itself, because Fpush is the hypotenuse for this right triangle. All right. Same algebra step. However, Fpush though is 82 newtons. Okay. So cosine here is 23 times 82, and if you simplify on your calculator, you'll get 75.48 newtons. But here I highlight the negative sign again because if you look at my diagram, Fpush in the x direction is pointing leftward, which suggests that you should include a negative sign. All right, and then for the y direction, Fpush in the y direction here is pointing downward, and then it's the opposite leg, so we do sine. Sine of what? Sine of 23 because that's the angle given. And if you do all the algebra step again, you get a value of 32.04, and it's negative because it's pointing downward. All right, so that or those would be your answers for part B. So these are your four answers: Fpull x, Fpull y, and then Fpush x, and then Fpush y. Okay. All right, I'm gonna move on to C, D, and E. C asks us to find the magnitude and the direction of the normal force. Well, if it says normal force, I want to focus my attention in the vertical direction. So I want to list everything out again for you. Fpull in the y direction points upward. Fpush in the y direction is pointing downward. And then I want to label my f of g. And my f of g here is just mass times gravity. And the acceleration due to gravity of the surface of the planet is negative 9.8. And then if you simplify that, you get f of g is negative 245 newtons. Well, it's common sense. F of g is pointing down the page, so it has to be negative, right? So whether you find the magnitude or not, it's important that you pay attention to the fact that arrows have directions, or excuse me, vectors have directions. So make sure you include the negative sign when and where appropriate. All right, and then it asks for f of n. In this case, f of n is going to point up perpendicular to the surface. So here's your surface, and it's perfectly horizontal. Therefore, f of n is perpendicular to that, which in this case suggests that it lies on the y-axis. So here's f of n, and then that's it. Okay. Well, to do f of n, I'm going to use the information I previously found in the y direction because f of n is in the y direction. So I crop out the x information because I don't need it right now. So keep in mind, these are the values that I'm circling back and forth. These are the values I need. Fpull y, and then I also need Fpush y. Okay. Well, I'm going to set up Newton's second law for the y direction. I'm going to expand it. On the right side, ay is equal to 0 because the box is to remain in contact with the surface for these types of problems. So it does not accelerate up or down. So ay is equal to 0. Do not plug in 9.8. Yeah, 9.8 is only if it's like free falling, which would suggest that it's not hitting a surface, like it's just falling in the air. But this is not falling. It's just being dragged across a horizontal surface. All right. So here are four terms: Fn, Fpull y, Fpush y, f of g. I will take it from positive. Fn is going to point upward, hence that's Fn. Fpull y is also pointing upward. I kept that as positive. And then Fpush y is negative. The red dashed line here where my cursor is going back and forth, that's pointing downward. So I already introduced the fact that it's pointing downward by using a negative sign. And in addition, f of g is also pointing downward. So I'm also going to say that that's negative already. So I like to introduce my negative sign from the get-go. Okay. Well, to solve for fn, we can just simplify it. Well, m times 0 on the right side is 0. So to get fn by itself, I need to move these three terms to the other side of the equal sign. So negative fg will become positive fg. Negative f push y will become positive f push y. And then positive f pull y will now become negative f pull y. I'm just going to plug values in. F of g here is 245, and then f push y is 3204, which is right here. Watch where I'm circling, okay? Now, in case you're not listening, what I'm circling shows negative 32.04, but keep in mind that I've already introduced the negative sign from the get-go, okay? Likewise with f of g, right? F of g on the screen here is negative 245, but I already said that it's negative in my second statement here. So when I get to this, as I took my work down, really, I'm just plugging my magnitude because the negative signs have already been accounted for. Because if you don't pay attention and you plug here negative 245 and negative 32.04, you'll screw yourself over. All right, so decide when you want to introduce those negative signs. I like to get it out of the way first. All right, so this is positive 245 for that reason. This is positive 32.04 for that reason. And then here, F pull in the y direction is 39.12, and it's right there. Okay, so let's go ahead and finish this. If you simplify this on your calculator, you should get a value of about 237.92 newtons. And here I include the plus sign because in the statement it asks to find the magnitude and direction of the normal force. So the magnitude would be 237.92 newtons, and then the direction would be positive because it's pointing up from the floor. All right. So that's part C. Part D asks us to find the magnitude and the direction of the acceleration. Well, in this case, I want to get rid of the y information on my screen here. Okay. I know for a fact that it doesn't accelerate up or down. It just accelerates leftward using common sense because both these applied force, F pull and F push, both have horizontal components that are pointing leftward. So I'm going to go ahead and redraw the stuff on the screen for you. F pull in the x direction is going to point left. F push in the x direction is going to point left as well. So here I have two components that are pointing leftward, which would suggest the acceleration is going to be left as well because your acceleration follows your net force. In this case, your net force is negative because it's both pointing. Oh, they're both pointing leftward. Okay. So net force in the x direction equals max. Well, if you look at this diagram properly, net force in the x direction just has two components, F pull x and F push x. So I'm just going to go ahead and state it. Once again, I'm already telling you that it's negative. A negative F pull x, and then there's another negative F push x. That equals to max. So if I plug in values here, I carry down the information that I previously calculated in the other parts. F pull x here is negative 51.91. F push x is negative 75.48. So therefore, using common sense, you have a negative value, and then you have another negative value, which will give you a bigger negative value, right? So I'm just going to plug in, once again, just the magnitude. The negative sign is already there. So I'm going to put in 51.91, which is what the answer is here. And then you can add a negative, or here I'm just subtracting a positive, which is the same thing. So if you sum it up, it makes a bigger negative number, right? So make sure you pay attention to the outcome. It has to make sense. So I have negative 127.39, and then that equals 25 times ax. And to get ax by itself, I would divide both sides by 25. So my acceleration here is going to be negative 5.1 meters per second square. And I need the negative sign because in part D, it says the magnitude and direction. So the magnitude, once again, would be 5.1, and then the direction would be negative, which would imply that the system is moving leftward, which makes sense. All right, let's go ahead and do part E. Part E asks us to find the coefficient of friction between the box and the floor if the system now accelerates at 5.7 or 5/7 of the acceleration calculated in part D. Well, we just calculated the acceleration in part D, which is negative 5.1. So it's telling us now that it's going to accelerate slower because 5/7, is a small, or it's a fraction of the whole, right? So therefore, I'll just go ahead and cross out the word smooth here in the diagram because now it has friction. Because there's friction for this one, I know f of k is going to point rightward because the system is being pushed and pulled to the left. Therefore, f of k opposes it. Opposing the motion in this case would be pointing right. So f of k, and actually for this problem, it's actually positive. Okay, so don't get into the habit where f of k is negative. F of k can be negative or positive based on what the system is doing. In this problem, the system is being pushed and dragged leftward, so therefore f of k once again is pointing rightward. Well, to find the coefficient of friction, I need two things. I need the f of k and I need f of n. right? Well, I already know f of n from part C. If you have been keeping up all along, part C says determine the magnitude and the direction of the normal force. Well, I already have the answer to that from part C. Here, I don't have what f of k is because f of k just got introduced. Well, to find f of k, I just need to set up the information in the x direction because f of k lies in the horizontal direction. So I'm going to set up net force in the x direction again, which equals to max. However, now there's an additional force in the x direction, which is f of k. Before, there was only two, right? It was only f pull x and f push x. Now you got three, which is the introduction of f of k. So just introduce it. Here, I have negative f pull x. Once again, the negative sign's already introduced. Negative f push x as well. And then here, f of k is positive, so I'm going to add that, right? Because f of k is positive, so that positive sign indicates that it's moving or it's pointing rightward. All right, so I'm just going to plug values in. Negative 51.91. That's because we already calculated earlier. And then f push x direction has a magnitude of 75.48, but it's also pointing leftward. And so those two negative signs will make a bigger negative. And then here, f of k left alone because that's what we need. Here, mass 25. The acceleration, well, I don't know what it is, but I know that's 5/7 of the acceleration previously calculated. So therefore, I just carry down 5/7. And the acceleration previously calculated in part D is negative 5.1. So don't forget that negative sign. If you forget this negative sign, you'll screw yourself over. Okay. Well, here I'm just going to simplify so you hopefully this makes the algebra easy on you. I have a negative value. I have a negative value that makes a bigger negative value, which is negative 127.39. I want to add that to f of k, and then if you plug in 25 times 5/7 times negative 5.1, you get negative 91.07. Now to solve f of k, well, that just combine like term. I want to move this negative 127.39 to the right side, which will make it positive. So therefore, here you have a statement that says f of k is equal to negative 91.07 plus 127.39. And if you plug that in your calculator, you'll get a positive 36.32 newtons, which makes sense, right? F of k in this diagram is pointing rightward. So the fact that I'm getting a positive answer tells me I'm doing my work correctly. So hopefully, keep in mind as you practice, your values has to make sense based on what the diagram is doing. All right. Other than that, I'm going to plug 36.32 in for f of k. I already know fn, which is positive 237.92 from part C. And if you simplify this on your calculator, you'll get a value of 0.15. So the coefficient here of friction, once again, has no unit, it has no direction. So the answer would just simply be 0.15. All right. I hope that helps. Stay nerdy. Don't be whack.